Good morning, dear participants, dear guests. We start our last section number 4, modern electrical and energy systems. So now I would like to invite Volodymyr Zinovkin, Alexander Salamacha, Yuri Krisan, Alina Kazarova, and Mykola Antonov to present on the topic of investigation of stator voltage oscillation in an asynchronous motor within a high frequency specialized electrical drive. Let me share my screen.
Dear participants of the conference, let me introduce to your attention the report on the topic Investigation of stator voltage oscillations in an asynchronous motor within a high-frequency specialized electric drive. High-quality steels and alloys are manufactured in specialized high-frequency induction technological complexes. The main elements of such complexes are the induction furnace, capacitive reactive power compensators, switching devices, and primarily the specialized electric drive. It consists of the three-phase asynchronous motor and a single-phase high-frequency synchronous generator. The interactions between the power elements of the induction complex are explained on the slide 2. During electrotechnological modes, voltage and current distortions occur as a result of reactive power compensation modes and changes in individual phases of electrotechnological processes. The latter lead to a series of non-stationary electromagnetic processes, such as partial loss of static stability and increased voltage of the synchronous generator. These modes have a corresponding impact on the asynchronous motor, which is intended to ensure the stability of the frequency of the synchronous motor. Numerous repetitions of the above-mentioned disturbances and stability modes lead to the formation of non-stationary electromagnetic processes in the motors and the accumulation of cumulative processes. These processes result in reduced reliability and emergency failures of the motors. As an example, fragments of motor damage in the power supply system of induction furnaces are shown on the slide 3. In certain dynamic modes, the output phase voltages of the PWM frequency converter are sources of the voltage distortions. Such a lowered nature of the PWM electric drive leads to the following undesirable phenomena and consequences: increased additional losses in the electric drive and technological line, overheating of windings and power cables, deterioration of dielectric properties of insulation materials, accelerated aging of the electric drive installation, increased overall background noise levels and in the octave frequency spectrum, development of magnetostrictive phenomena in the magnetic system and individual structural parts. And the last one, resonant ferromagnetic and mechanical phenomena. The purpose of this paper is to develop a method for feed-forward compensation of stator voltage distortions in a synchronous motor as part of specialized electric drive, which are introduced by power filters and taking into account the dynamic parameters of the load. The problem statement is explained using a functional diagram of the compensation circuit for the imperfections of the passive power filter, PPF, which is shown in the slide 4. The solution to the scientific problem is based on the physical mathematical model of the compensation circuit aimed at eliminating the shortcomings of PPF as presented on the slide 5. In analytical form applicable to the studied model and further theoretical investigations, the two-phase signal is conveniently represented by Formula 1. After passing the two-phase signal or its equivalent three-phase signal through a filter, the equivalent two-phase signal takes the form of the expression 2. To eliminate distortions, it is advisable to use a compensator with a predictive filter, FFC, which should have frequency characteristics as it's shown in the Formula 3. In this case, the output signals taking into account expression 1 are transformed into the form of the expression 4. To obtain the transfer function of PPF, let's consider one phase of the system, frequency converter, PPF, and a synchronous motor, which is shown on the slide 6. The asynchronous motor is represented as variable RR load, the parameters of which depend on the electromagnetic and structural characteristics of the motor, its operating mode, and sleep. The transfer function of the system takes the form of expression 5, which corresponds to the frequency characteristics 6. The operating mode of the compensator with a lead filter corresponds to the equation 7. The simulation of the feed-forward filter compensator was carried out according to the system shown on the slide 7. The model represents the following sequentially connected components: a variable frequency signal source, a filter compensator, coordinate converter, PWM signal generation block, LC filters, and RR load simulating the asynchronous motor. Before the LC filters, in the PWM signal generation block, noises imitating distortions introduced by the PWM with an amplitude twice the amplitude of the useful signal and a frequency of 4 kHz were added to the main signal. The source generated a periodic two-phase signal with an amplitude of 100 volts and a variable frequency, which changed as shown on the slide 8 above. At the bottom of the slide, the simulation results of the FFC are shown, from which it can be seen that there is a discrepancy between the desired and output signals in the alpha and beta channels. As the simulation results show, the proposed compensation filter is operational over the entire frequency range of plus minus 50 Hz. At the same time, there is a 3% error in the amplitude due to noises imitating PWM modes. Thus, the proposed compensation filter reduces the amplitude of noises and simultaneously eliminates distortions of the main harmonic in amplitude and phase. The simulation was carried out with the parameters that are shown on the slide. The effect of distortions on the electromagnetic parameters of the motor model is shown on the slide 9. It can be seen that with a change in the electromagnetic moment of the electric drive, current distortions are formed in the stator and the rotor rotation speed partially changes. This indicates the consistency of electromagnetic and electromechanical processes in the drive and therefore affects the static stability of the synchronous generator. Thus, it is shown that to ensure the reliable operation of the synchronous motor, it is necessary to provide compensation or to preempt undesirable processes formed in the electrical technology complexes. The whole conclusions on the paper are presented on the slide 10. We would like to underline that the developed method of feed-forward compensation of stator voltage distortions in a synchronous motor as part of a specialized electric drive introduced by power filters allows correcting real load parameters and ensuring the stabilization of operating modes of single-phase synchronous motors. Thank you very much for your attention.
Thank you for your presentation. It was very interesting and informative talk. Now, are there any questions from the audience? Alexander, please.
Hello, do you hear me?
Yes.
Thank you. I have two questions. Tell me, please, what is the nature of such voltage oscillation in stator? And second question, what parameters did you take into account during the voltage oscillations study? Thank you.
Alexander Salamacha. Please, we wait on your answer.
Okay, I have no questions.
No, just a second. We
Ah.
need for Alexander too. Alexander Salamacha, if you hear the question, would you please answer? I see that he is with us, but
Maybe I answer the question.
no answer.
Maybe other courses answer.
Тогда говори.
Maybe we'll wait and he will join us and can answer a bit later if you don't mind. When he will have the opportunity to answer, because we expected for him. And now maybe we can continue with the next presentation and then we can return if you don't mind.
Now I would like to invite Konstantin Bazilio, Vitaly Andrienko, Viktor Antoniuk, Yulia Bondarenko, and Maxim Bondarenko to present on the topic modeling the electrical impedance of a spherical piezoceramic device for microelectronic systems.
Congratulations to the participants of the SIEMS conference. I would like to present a report on the topic Modeling the electrical impedance of spherical piezoceramic devices for microelectronic systems. The focus of this report is an interdisciplinary problem that combines mechanics, electronics, and material science. The relevance of the study is clearly outlined. Modern microelectronics requires miniature energy-efficient devices with stable characteristics. At the same time, it is the spherical shape of piezoelectric elements that makes it possible to reduce local loads and increase the accuracy of diagnostics, which justifies the need to search for new mathematical models. The need for such a study lies in the need to develop universal mathematical models to accurately determine the impedance of spherical piezoceramic elements, since the available models do not fully take into account their geometry and dynamic conditions, which complicates the integration of such elements into CAD systems. The purpose of the study is to build a mathematical model of the impedance of spherical piezoceramic shells, taking into account geometric and material factors. Such a model should reflect the real influence of physical and mechanical parameters, shape, and operating conditions on the electrical characteristics of piezoelectric elements used in microelectronic systems. To achieve this goal, the work solves three key tasks. Analytical analysis of the dependencies of electrical impedance on geometric, material, and electrical parameters of spherical shells is performed. Numerical modeling of impedance frequency characteristics is carried out with further comparison with experimental data. The functional features of the operation of spherical piezoceramic elements are investigated, and their advantages and limitations in comparison with disc and cylindrical analogs for use in sensory, diagnostic, and energy microdevices are substantiated. Thus, the presented research is aimed not only at formalizing the theoretical model, but also at its practical application in conditions close to real operation. A closed piezoceramic shell consists of two hemispheres connected by glue. Both hemispheres are made of PZT19 piezoceramic, but are polarized in opposite directions. In the figure, the polarization directions are indicated by bold arrows with the symbol P. We agree that the direction of polarization of the upper hemisphere is positive. The surfaces of the hemispheres are covered with electrodes. Since the adhesive bond is non-conductive, the inner surfaces of the hemispheres are electrically connected by a conductor before bonding. The electric potential difference generator is connected to the sphere in such a way that the potentials in the upper and lower hemispheres at any given time have charges of the opposite sign. In the model of harmonic oscillations of piezoceramic shell polarized in opposite directions in the upper and lower hemispheres, split notations are used for electric field intensity and displacement, with corresponding superscripts plus and minus. This allows to correctly take into account the differences in the electromechanical state in the two parts of the sphere. Substitution of these expressions into the equation of harmonic oscillations makes it possible to obtain conditions for the equality of amplitudes of radial displacement of particles within the entire sphere, which provides a physically consistent model of centrally symmetric oscillations. Thus, the presented mathematical model describes electrical displacement, field strength, and mechanical stress through a system of generalized equations that make into account the geometric symmetry of the shell and the opposite polarization of its halves. This creates the basis for the accurate determination of the electrical impedance of the piezoceramic shell under dynamic load conditions. Within the framework of the mathematical model, the electric potential of a total electric field in a spherical piezoceramic shell is considered, which is determined by the dependence between the electric field and the potential gradient in the upper and lower hemispheres. A generalized expression for the potential as a function of the radial coordinate argument is derived, taking into account integration constants and key physical parameters. Such a model takes into account electromechanical coupling coefficient, effective modulus of elasticity, dielectric constant, as well as elasticity, piezo modulus, and dielectric constant tensor. All these parameters provide an accurate description of the dynamic behavior of a spherical piezo structure under symmetrical radial oscillation, which is key to predict impedance characteristics under real operating conditions. A system of algebraic equations was also formulated to determine integration constants based on boundary conditions for electric potentials. As a result, an analytical expression for electrical impedance was derived, which at small values of the wave parameter is equivalent to the impedance of two capacitors connected in series. Thus, a closed spherical shell of two connected hemispheres have the same resonance characteristics as a solid spherical piezoceramic structure, which allows this model to be used to accurately predict the electromechanical behavior of such elements in microelectronic systems. As a result of mathematical modeling, the electrical impedance of a spherical piezoceramic shell, which is used as an element in microelectronic devices, was investigated. The calculations were made for the shell made of PZT19 material, taking into account its characteristic parameters given on this slide. In this case, the frequency characteristics of the impedance are represented in terms of a dimensionless wave number gamma r, or a corresponding dimensionless frequency that takes into account a characteristic timescale. This approach allows to evaluate the frequency behavior of impedance and adapt the results for use in microelectronic device systems design. The function f from gamma r, which is represented in the graph and this slide, and describes the behavior of a spherical piezoceramic shell in the frequency range. Thus, knowing the frequencies of resonance and anti-resonance mass, volume, and dynamic capacitance of the shell, it is possible to calculate the key integral parameters of the piezo material: modulus of elasticity, coefficient of electromechanical coupling, density, dielectric constant, as well as piezo modulus. The variation of the f from gamma r function modulus shown in this graph allows to estimate the dynamic electrical capacitance of the shell under conditions of special oscillations, which is an important step for identifying the real characteristics of the piezoceramic material. Thus, it was found that spherical piezoceramic cells have a number of advantages over cylindrical and disc analogs, which makes them promising for use in microelectronics, diagnostic, and sensor systems. In particular, they demonstrate a higher quality factor, lower electrical impedance, a wider operating frequency range, increased stability to strain, and lower sensitivity to local resonance, which improve the accuracy and quality of oscillation generation. In the course of the study, mathematical models were analyzed and analytical expressions were obtained to calculate the electrical impedance of spherical piezoelectric shells. The constructed model describes the dependence of impedance of the cyclic frequency and a complex of geometric, physical, mechanical, and electrical parameters, allowing to determine both the impedance and amplitude values of current and charge at the electrodes under the reverse piezoelectric effect. This provides a complete description of the harmonic axisymmetric oscillation of the spherical shell. The obtained results are based on experimental data collected during the research project development of an automated ultrasonic system for extracting plant raw materials in the production of multi-nutrient functional beverages for rehabilitation and prevention of post-traumatic stress disorders. Thank you for your kind attention and interest in the research topic.
Thank you for your presentation.
Yes, we have the question, is there somebody from the authors of this scientific work online with us?
Виталий Андриенко, Виктор Антонюк,
Юлия Бондаренко, Максим Бондаренко. Is there
online with us.
no, I can see. Okay, maybe they will join us to attack notes, or maybe they have some troubles with joining. Let's continue and not wasting our time. So the next presentation on the topic, peculiarities of determination of inductance of an induction synchronous electromechanical converter in short circuit mode by 3D field simulation methods. Of the authors, Mikhailo Kotsur, Dmitro Yerambash, Igor Kotsur, and Yulia Bezvetnya. So we will start the video records and then we'll have some questions.
I welcome all conference. Participants. The topic of the report, peculiarities of determination of inductance and of an induction synchronous electromechanical converter in short circuit mode by 3D field simulation methods. Speaker Mikhailo Kotsur. The existing methods of determination of inductive parameters of stator and rotor windings of electromechanical converter are applicable only for popular design of electrical machines such as induction electric machines. In addition, these methods are based on empirical dependencies and have a higher error of calculation. For other classes of electrical machines, in particular induction synchronous electromechanical converters, such as methods are not available. This determines the relevance of the development of new approaches to determine the inductances of special for new designs of induction synchronous electromechanical converter on the basis of modeling of special electric and magnetic field, taking into account the design features, non-linearity of electrophysical and magnetic properties of materials. This will ensure computational efficiency and accuracy of the obtained results. The aim of this work is to develop a new methodology and techniques for determine the inductive components of the armature and rotor windings of a new design of the induction synchronous electromechanical converter based on the three-dimensional mathematical modeling methods of time-dependent electric and magnetic field, taking into account the design characteristics, non-linearity of the electrophysical and magnetic properties of the structural materials in its active part. To perform numerical field calculation of electromagnetic processes of the experimental prototype induction synchronous electromechanical converter in the short circuit mode, a computational special geometric model shown in figure 1. To study the non-stationary electromagnetic processes of the induction synchronous electromechanical converter prototype in the mode of the bracket rotor, a coupling of a system of non-linear partial differential equation. Number 1. Additionally, the differential equation add the equation number 2, number 3, number 4 for describe the external boundaries of the special domains, add two initial conditions, the combination of the power supply with the geometric special computation domain of the induction synchronous electromechanical converter armature, taking into account the connection of coils in accordance with the circuit implementation of the armature was implemented using COMSOL multi-physics software. Science is the armature and rotor windings of the experimental prototype are computational subdomains of the field model. Their parameters can be determined through the magnetic field energy active losses of the active part of the electromechanical converters, and this describe with help equation number 5. To determine all the components of the inductances of the armature and rotor windings of the electromechanical converter, we will compose equation for the complete flux leakage of the windings. According to the classical theory of electrical machines, the equation for complete flux leakage of phases A, B, and C of the induction synchronous electromechanical converters armature winding will be as below. This described with help equation number 6, and also for rotor windings with help equations number 7. To determine each of the components of the complete inductances of phases A, B, and C, it is necessary to represent the special computational domain in the form of two separate subdomains: the separate active part of the armature and the rotor of the electromechanical converters. To determine the leakage inductance of the phase armature windings of the experimental prototype, the authors proposed to switch on each of the phases of the armature winding in turn to determine the mutual inductances between phases A, B, B, C, and C, A of the electromechanical converter armature are switching on in a group. This approach makes it possible to apply the principle of superposition for the electromagnetic field in accordance with the Biot-Savart law to the computational domain of the active part of the inductance synchronous electromechanical converter armature. Their calculated values of the leakage inductance and the mutual inductances between the phases of these electromechanical converters armature windings shown in the table 1. This to determine the leakage inductance of the entire short-circuited coil, it is necessary to determine the leakage inductances of each section of the mutual inductances between the winding sections of the coil. In this case, the winding sections forming the phase coil A were switched on independently and in a group respectively. The table 2 shows calculated values of the leakage inductances and the mutual inductances of the rotor winding section of the phase A of the induction synchronous electromechanical converter according to numerical modeling. And table 3 shows the estimated values of the leakage inductances and the mutual inductances of the phase coils electromechanical converter rotor windings. The proposed approach can also be used to determine the main inductances between separate phases coil group of the armature windings and short-circuited phases coil of the inductance synchronous electromechanical converter rotor windings. Since the phases coil group of the armature windings are symmetrical with each other, the simulation was carried out with phase A of the armature bearings constantly switched on and phase coils A, B, C, D, F of the rotor windings switch on in a turn. The main inductances for each of the armature phases A, B, and C, and the corresponding rotor phase coils will be the same. Based on the results of the three-dimensional modeling, in Table 4 are shown the calculated values of the main inductances between the phases coil group of the armature windings and the phase short socketed coils of the induction synchronous electromechanical converter rotor windings. Thus, according to the proposed approach to the decomposition of electromagnetic processes during single and group switching on the phase coil group of the armature windings and phase independent short socketed rotor windings, it is possible to determine with high accuracy all components of the inductances. Conclusion. A technique is proposed for determining the leakage and mutual inductances between the phases of the armature and rotor windings, as well as the main inductances between the armature and rotor windings of an induction synchronous electromechanical converter. This technique is based on the method of decomposition of electromagnetic processes using various combinations of mains power supply to the armature phases windings without and with the presence of the active part and rotor phase coils of an induction synchronous electromechanical converter. To implement the developed technique, a mathematical three-dimensional circuit field model of the induction synchronous electromechanical converter was proposed, which also determined electromagnetic parameters with respect to the supplied voltage from a power supply system, taking into account the design features and connection scheme of the armature and rotor windings, non-linearity of magnetic and electrophysical properties of materials, surface, age, and other effects. With the help of these techniques, the values of leakage inductance, mutual inductance between winding phases, as well as the main inductance between armature and the rotor windings of the induction synchronous electromechanical converter prototypes were determined with high accuracy. This makes it possible to determine the total flux leakage in the armature and the rotor windings of the induction synchronous electromechanical converter, as well as to further develop and supply a simple mathematical models which is based on simple first-order differential equations. The proposed technique can also be applied to any class of electrical machines. So, thank you for your attention. Good morning, please, question.
Thank you, Mikhailo, for your presentation. Now,
we'll have some questions. Maybe there are some questions from the auditory. Maybe somebody would like to ask. No? Okay, so the question from
Mikhailo, any modeling and numerical calculation required experimental confirmation. How you compared the modeling result with experimental data?
The three-dimensional model fully corresponds to the experimental prototype, which was developed and tested in the laboratory of our university. The experimental tests were carry out both for the entire electric machine and separately for its armature in short circuit modes. The modeling error was determined by the current errors of the armature winding of the testing prototype.
Okay, thank you. One more question. So you claim that your developed 3D field model takes into account nonlinear magnetic and electrophysical properties of materials, surface and edge effects. So what do you mean by these edge effects, and how important is their consideration?
Edge effects appear as a result of magnetization of the end zone of the armature and rotor cores by the frontal parts of the windings of this prototype. This leads to an increase in the energy of the magnetic fields, and therefore the reactive power and inductance of the windings. The higher the rated power and the large the dimensions of this type of machines, this stronger the influence of edge effects. Therefore, it's very important to take into account the non-linearity of the magnetic properties of active materials when determining the component of inductance.
Okay.
Thank you. I have an extra question.
Okay.
Mikhailo, what are your future plans regarding this research?
Future, the next studies will be aimed at developing a simplified mathematical model for induction synchronous electromechanical converters, which will be built on equivalent sockets. Such models require the determination of all components of the inductance of the windings. So this was done in this work.
Thank you, Mikhailo.
Yes, and before we continue and we'll listen the next presentation, let me to switch to Ukrainian. So, мене питання, Володимир Зиновкін, чи вийшло у вас під'єднатися і чи можете, чи нормально у вас зі звуком? Можете включити мікрофон. Володимир Зиновкін.
Алло,
Так, ми вас чуємо.
да, добре.
Одну секундочку. So, я б попросила...
Олександр Шрам, can you repeat your question in Ukrainian?
Щодо першої доповіді повинен був Олександр Соломах, у нього проблеми з мікрофоном, звуком, тому, на жаль, він не зміг доєднатися. Питання, будь ласка, повторіть українською.
Thank you. It's very good for me that I was write down my questions.
Окей.
Tell me, please, what is the nature of voltage oscillations in stator? And what parameters did you take into account during the voltage oscillations study?
Чи не могли б ви, будь ласка, українською мовою продублювати питання?
Okay. I can translate my questions.
Будь ласка.
Скажіть, будь ласка, яка природа виникнення коливань напруги в статорі? Чи це зміна навантаження, чи це, може, якісь інші фактори? І друге питання в розвиток. Які параметри ви враховували під час дослідження оцих коливань напруги?
Мгм. Добре. Значить, я відповів наступним чином. Ці коливання за своєю природою виникають унаслідок цілої низки технологічних процесів. По-перше, це коливання технологічного процесу. У процесі технологічного режиму є опір індуктивний і реактивна складова. Внаслідок чого змінюється процес компенсації реактивної потужності за рахунок режимів компенсаторів реактивної потужності, тобто конденсаторів. Це перший чинник. Другий чинник. Під час зміни реактивної складової потужності відпрацьовують певні секції конденсаторних батарей. І внаслідок комутаційних процесів виникають інші коливальні процеси. Вони дуже короткочасні, але частоти їх дуже не співпадають з промисловою частотою. Третій чинник. При директивному режимі печі напруга відповідає номінальним параметрам. При зміні режиму або зміні фази технологічного процесу відбувається часткове відключення печі під час переходу на інший режим, внаслідок чого на синхронному двигуні підвищується напруга, що призводить до перенавантаження по магнітному потоку. Тобто це процес, який внаслідок оцих технологічних дій призводить до перевантаження по магнітному потоку. І четвертий наслідок. Внаслідок оцих всіх процесів змінюється статична стійкість генератора. І таким чином, внаслідок дії, вони не контрольовані. І вони виникають внаслідок дії цілих технологічних оцих дій. Тому...
Володимир Васильович, вибачте, будь ласка, так, а здається, що мова йшла про двигуни, а зараз генератори з'явилися, чи...
Я зараз відповідаю про генератор. Про
Добре, дякую. Дякую, Володимир
генератор.
Васильович.
Так. Наступне питання.
Немає, ви так дуже докладно це питання розглянули, що і, ну, відповідно, ви відповіли на друге моє питання, які параметри там і напруга, і реактивна потужність, і режими роти компенсуючих пристроїв, і багато-багато інших. Нічого, що я українською.
Основним чинником є активна складова потужності. Тобто, звичайно, це відомо, що активна складова потужності призводить до ефективності виконання технологічного процесу. Тобто, виконання сплавів оцих, як вони спеціалізовані сплави там, температурні режими. От. Основний чинник – це активна складова.
Добре.
Якщо існує, це вам повинно навіть більше відомо, якщо існує реактивні складова, то це ємність, індуктивність там і все. То це призводить до скорочення, зменшення теплових режимів внаслідок оцієї активної складової зміни. Ну, а інші чинники – це потужність, частота, напруга і струм. А далі там уже це побочні, це реактивний струм,
Дякую,
ємностний
Володимир.
струм
Добре,
і
добре,
так
детальна
далі.
відповідь.
Таймінг.
Да.
Не вистачить часу для
А,
інших виступів.
Олександре, у вас влаштовує відповідь, так? Можемо продовжувати.
Completely. Sure.
So thank you. Thank you, Volodymyr, for your answer. So let's move on. Let's continue. And the next presentation on the topic efficiency, evaluation of high power dual system wind turbines of the authors Petro Andrienko, Dmitry Alexeyevsky, Viktor Greshta, Alexander Biznyakov, and Olga Nemikina. As usual, we'll start the video records and then there will be some questions.
The name of the article is Efficacy Evaluation of High Power Dual System Wind Turbine. The second slide, you can see introduction and main problems. It is known that one of the modern trends in development of electric power engineering is the use of renewable energy sources such as wind power, solar, and so on. Wind energy is widely available and has significant potential. By now, 12 megawatts wind turbines has been developed and are in operation, and more powerful wind turbines are being developed. A significant disadvantage of wind turbines is a presence of mechanical gearboxes in frequency converters, which significantly reduce the efficiency or very great mass of generators in Galley's wind turbines. To eliminate certain disadvantages is possible by using wind turbines with aerodynamic multiplications, WTAM, in which generators with additional secondary wind turbines are arranged on non-turn parts of the main wind machine blades. This enables to use high-speed generators, which significantly reduce their total weight and cost compared to lower-speed generators. The application of synchronization generator in TAM does not require the use of frequency converter. However, it should be noted that an increase in the VTAM power, the weight of generators increase as well. In the third slide, you can see aim and research task. The purpose of this work is to develop and substantiate conception to construct dual system wind turbines that would enable to increase the efficiency of more than 5 megawatts wind turbines. This is due to the first, reducing the total mass of generators' active components. The second, increasing their efficiency. And the third, decreasing the installed capacity of convectors compared to extensively used gearless wind turbines with lower speed generator. Slide 4, you can see structural diagram of dual system wind turbine. Figure 1 shows front view and side view. High-speed generator 5 with secondary wind machine 4 are arranged on non-turn parts of the blades 2, like WTAM, and a low-speed generator 7 conjunct to the main wind machine axis. Low-speed generator is connected to the network via frequency converter 8. Note that the frequency converter contains a regulator for distribution the power between generator 5 and 7. On the slide 5, you can see functional diagram of the dual system wind turbine. The motion dynamics of the generators in dual system wind turbine is described by practically the same system of differential equation 1 as in the WTAM. On the sixth slide, you can see analysis of change trend in the mass of dual system wind turbine generators. To determine the mass ratio of wind turbine generators to the corresponding mass of a single generator conjunct to the axis of the main wind machine, given wind turbine power, we will use the following expression. It is expression 2. Using the moment ratio from the system of equation 1, the total electric power will be determined by following expression. It is the expression 3. We obtain the total relative mass value of lower speed generator of gearless wind turbine to mass of dual system wind turbine generator. It is the expression 4. Slide 7, you can see the result of this article. Figure 3 shows families of dependencies relative G equals function of KAM for series of value K1 equals constant. The coefficient K1 changes from minimum value 0.25 to maximum value equals 1. Figure 4 shows families of dependencies relative G equals function K1 for series of constant value KAM. Analysis of graphical dependencies shows that the value of relative G changes monotonically under changing K1 and increasing under increasing K1 and KAM. Since the function figure 3 and function in the figure 4 do not have extrema, then the specific value of K1 and KAM can be selected based upon technical and economical analysis and design constraints, taking into account mass of generators. A significant relative reduction in total mass relative G under increasing KAM at K1 equals 0.5 to 0.75 is due to large mass of lower speed generator. On the slide 9, you can see three main operating conditions due to operating principle of the dual system wind turbine, which enables to increase the efficiency of their electromechanical system. On slide 11, you can see the first operating mode. This operating mode is close to nominal 1. The efficiency of the system is determined by the ratio 5. For certain values of efficiency and coefficients K1 and K2, ratio 5 is transformed into expressions 6 and 7. The efficiency is higher for the specified system in this expression. On this slide, you can see the second mode of operation in the dual system wind turbines. Generation by the secondary generators at wind flow speed when the power developed by wind machine is less or equal to power of secondary generators. In this case, efficiency has the maximum value. On this slide, you can see the third mode of operation dual system wind turbines. Generation at wind flow speed less than 0.5 nominal. The energy is generated by generator conjunct to the main wind machine, providing maximum power production. In this case, efficiency is determined from the 8 ratio. Note that this operation is close to nominal one, which also contributes to increased efficiency compared to wind turbine with one powerful generator. On this slide, you can see conclusions to these articles. The first one. The research findings confirm a significantly high potential to increase efficiency of converting wind flow energy into electrical one in high-power dual-system wind turbines. The second, we obtain the ratio that enable us to establish an interrelation between the mass of active materials, the ratio of generator powers and multiplication factor of dual system wind turbine.
Thank you for your presentation.
Do we have the authors of this scientific work here with us online who will be answering the questions?
Петро Андриенко, да, вот это Дмитрий Алексеев.
Yeah.
Кафедра ЕЕ, ЭТР.
Yeah. You are here.
Okay. So if there are some questions from the auditorium, maybe somebody would like to ask. Welcome. If somebody have some questions.
Please, your
No.
question.
Okay, then we will ask. So the first question is, how is power distribution between generators ensured in a dual system wind turbine?
A distribution of power between generator is provided using a frequency converter with the help of power regulator according to the speed of primary wind flow.
Yes, one more question.
Olga, please explain what factors make it possible to increase the efficiency of dual system wind turbine.
The efficiency of dual system wind turbine is increased because of the fact that the major part of wind flow power is conveyed by subsystem with aerodynamic multiplication, generator without frequency converter with which have a maximum efficiency.
Thank you.
Maybe somebody else would like to ask. If no, then we can continue. So if there are questions, so you are welcome. If not,
Last presentation on topic methodology for determining the optimal operating mode of energy storage system in industrial enterprises. Автors Alexander Schramm, Katerina Bratkovska, Yulia Liush, and Metro Politaev.
Good day, everyone. Today I'll be present on the methodology for determining the optimal operation mode of energy storage system in industrial enterprises. The global energy sector is rapidly changing due to climate change and carbon reduction efforts. Many countries, including Ukraine, are facing challenges as they transition to cleaner but unpredictable sources like solar and wind. Energy storage systems are crucial in storing electricity during low-cost periods for use during expensive peak times. This study aims to determine the optimal times for using ESS in industrial enterprises. Key energy trends include integrating renewables, distributed generation, microgrids, and smart grids. In 2018, Germany has 125,000 ESS with a total capacity of over 1,500 megawatt-hour. In the USA, 28 gigawatt of 4-hour storage can meet peak electricity demands. This trend shows the growing importance of ESS in balancing renewable energy and managing costs for industrial enterprises. The aim of this study was to develop a method for determining optimal times for charging and discharging ESS in industrial enterprises. Our approach involved analyzing daily electricity consumption patterns, identifying periods of minimum and maximum tariffs, calculating the best time for charging and discharging ESS. By charging storage systems during low tariff hours and discharging them during peak tariff hours, enterprises can minimize their electricity cost while maintaining operational efficiency. The mathematical model used in this study calculates the total electricity cost based on several factors, including early consumption, storage capacity, and various electricity tariffs. To find the optimal times for charging and discharging ESS, we use the equations you can see on this slide. The both equations represent the vector form of the model. For example, these formulas show how the base consumption is adjusted by charging and discharging energy storage system, depending on the price situation. And to calculate early price for imbalances, we use statistical data on the early electricity consumption by the enterprise for 2023 and the cost of the electricity on the day-ahead market according to the state enterprise market operator. The first set of results compares the enterprise's electricity consumption with daily market prices. As shown in graph 1, the peak consumption happened between 8 a.m. and 11 a.m. and again from 7 p.m. to 12 a.m., aligned with high electricity tariffs. By charging ESS during low tariff hours such as between 2 a.m. and 5 a.m. and discharging them during peak tariff periods, the enterprise can reduce its electricity costs significantly. Table 1 displays the electricity consumption and the operational models of the energy storage system at different times of the day. This table highlights how the storage system helps to smooth out peak loads and optimize the cost of electricity by strategically charging and discharging based on tariff fluctuations. The second graph shows how the electricity tariff changes. This helps to find the best time to charge and discharge ESS. According to the graph, charging should happen when the change in the tariff is zero, and discharging should take place during the highest tariff points. This helps to lower energy costs overall. Graph 3 displays the difference between forecasted and actual electricity consumption. It also demonstrates how the implementation of energy storage system helps to reduce imbalances in electricity consumption. By resolving this imbalance sought energy storage, the company can lower its total energy cost. The final results present in Table 2 shows the monthly reduction in electricity expenses after implementing ESS. The saving range from 2.83 to 4.82% per month depending on electricity usage patterns and tariff fluctuations. This ongoing saving highlights the efficiency of the proposed energy storage strategy for industrial companies. In conclusion, usage of energy storage system has evolved industrial enterprises to achieve up to 5.4% in daily electricity cost reduction by optimizing charging and discharging times. This system also contributes to the overall stability of the power grid by reducing peak demand and preventing outages. ESS are essential for integrating renewable energy sources like solar and wind into the grid, which are often inconsistent due to weather conditions. As storage technologies continue to advance and become most cost-effective, enterprise will see even greater benefits in terms of energy saving and operational flexibility. Thanks for your attention.
Thank you, Alexander, for your presentation. There are any questions from the audience? Mikhailo, do you have a question?
I have a question. According to the mathematical model, the charging and discharging of the storage devices starts only in the hour corresponding to the minimum and maximum hourly prices for electricity. What do you think? Maybe the storage devices can start working early for greater economic effect?
Thank you for your questions. Yes, in this methodology, the starting storage device, so charging and discharge corresponding maximum and minimum of the price on day-ahead market. In the future works, we planning to correlate these parameters in our methodology and mathematical models, so that working of our energy storage system will be more efficiency and can more reduce payments for industrial enterprises.
Thank you very much for your answer. One more question from us. So, speaking about your methodology, so can you tell us what optimality criterion do you use, and if possible, explain why exactly this criterion was chosen?
Thank you. The main criterion for the optimization function that determine the operating modes of energy storage system is the minimum daily cost of electricity consumption payment in by the enterprise. This criteria was chosen because in other works, they not take into account the changing of the price in day-ahead market. So we trying to compensate this and analyze changing prices on day-ahead market and choosing appropriate operating modes for energy storage systems.
Okay.
Alexander, tell me, please, is there a plan to implement this methodology, and what action are required for this?
For now, scientists of Department of Power Supply for Industrial Enterprises is developing a new methodology for designing an innovative electrical power grid for industrial enterprises. And such grid includes distributed energy sources such as wind turbines, solar plants, energy storage systems, and others. And one of components of this approach is proposed methodology for determining the optimal energy storage system operation mode. So we planning to implement our work on our Zaporizhia region metallurgical power plants. Just plants.
For your answer.
So thank you very much for detailed answers. Thank you. Thanks to all participants of today's session for your presentation, for your answers. So this was the last presentation of this conference in general. And now we'll have a break for a lunch, and the closing ceremony will be at 1 p.m. So thanks to all for taking part in this conference, and stay safe, resilient, and continue doing what you are doing. So see you
1 p.m.
1 p.m. Thank you.
Thank you.